ever shipped a contract, felt good about it, and then got hit with a gas fee that made you question your life choices? Or worse, the contract works on testnet, works in staging, and then in production, you're chasing a bug that makes zero sense. Here's what's happening. While Ethereum attracted 16,000 plus new developers in the last years, 1 in 3 devs report confusion over EVM-specific concepts like gas optimization and opcode limits. In fact, many treat EVM as just Ethereum without grasping L2 nuances. The problem with that, when you don't understand the EVM, issues don't show up immediately. They show up later, as gas inefficiencies, edge case bugs, and architectures that fall apart under real usage. So today, we're opening the box. Hey, I'm Steve and welcome to the EVM World, a series where we break down how EVM systems actually work without turning this into a computer science class. Ethereum alone secures hundreds of billions of dollars in value, and every design decision in the EVM exists because of that responsibility. So today, here's what we're exploring together. First, what the EVM actually is. Second, how execution really works inside it. And third, why the ecosystem had to grow around it. By the end of this video, you'll be able to design smarter contracts, reason about gas costs before they surprise you, and understand where logic belongs on-chain versus off-chain. Let's start at the foundation. So what is the EVM? EVM powers the majority of smart contract activity across blockchains, executing over 70% of global Web3 transactions via Ethereum and 100 plus compatible chains. Think of it as a shared execution engine, not owned by a single computer, but run independently by every node on the network. When you send a transaction, you're not asking one machine to run your code, you're asking thousands of machines to run the same code using the same rules and reach, hopefully, the same result. It doesn't know who you are beyond the data you send. Contracts only see inputs like message.sender, message.value, and call data and act on those values. That's what the EVM defines. It specifies how smart contract instructions are executed, how storage and memory behave, and exactly how much each operation costs in gas. Because every node runs this same virtual machine, given the same inputs and the same block environment, they must all arrive at the same outcome. That's why determinism matters. Without it, consensus simply won't work. However, one key distinction to lock in, Ethereum is the network. The EVM is the execution engine. Today, EVM dominates Web3 execution, powering 60 to 90% of stablecoins and tokenized assets across Ethereum L1 and L2s, with L2s handling 58.5% of transactions. All right, now let's talk about execution. When you write Solidity, you're writing something human-friendly. But the EVM doesn't understand Solidity at all. It only understands a very small set of low-level instructions. So before execution, your contract is compiled into bytecode, a compact assembly-like format that EVM can actually run. Inside the EVM, execution feels less like running software and more like a checklist, one instruction at a time, with a meter running the entire time. That meter is gas. Every opcode costs gas. Every step is verified by every validating node, and if gas runs out, everything stops and rolls back. That's why failed transactions still cost money, and it's also why smart contracts feel rigid. Contracts can schedule themselves. They can't wake up later. Any delayed or recurring logic has to come from outside the EVM. That's because the EVM is optimized for fairness and repeatability, not developer convenience. Now, transactions. When a transaction enters the EVM, it's treated like a sealed envelope. The EVM opens it, runs the instructions in isolation, and then decides, does this fully succeed or does it fully fail? There is no halfway state. Think of a shared Google Doc where either all your edits apply or none of them do. That atomic behavior is powerful, but it also makes long multi-step workflows hard to fit inside a single transaction. Here's the analogy that ties it all together. Think of the EVM like a desk. The stack is what's in your hand right now, tiny and temporary. Memory is the desk's surface, useful during execution, wiped afterwards. Storage is the filing cabinet. It's persistent, but expensive. Every transaction clears the desk. Only what you deliberately store survives. And that's why storage costs so much. You're asking thousands of nodes to keep that data forever. Once you understand these constraints, Web3 architecture starts to make sense. The EVM is great at short-lived computation and long-term state. It is not good at history, analytics, time-based logic, or coordination. Because each execution is isolated, developers need ways to observe what's happening over time, react to events, and coordinate across transactions and chains. That's why the ecosystem grew outward. Indexes exist because on-chain state is not a query-friendly analytic store. Event listeners exist because contracts can't trigger actions themselves. Back-end systems exist because complex workflows don't fit inside one execution. So Web3 didn't become complex by accident, it became complex in response to the EVM's design. This is also where tools like Kwala fit in naturally. Contracts emit events, but they can't act on them. Kwala focused on everything after the execution, listening to EVM events, triggering workflows, and coordinating off-chain logic without custom servers. It doesn't hide the EVM, it works with how the EVM is built. You don't need to know opcode to be a great Web3 developer, but once you understand how the EVM thinks, you stop fighting it and start designing better systems. If you're building on EVM today, that perspective alone is worth a lot. And if this video helped you, subscribe to our channel and stay tuned for our upcoming videos. I'll see you in the next one.